All right, y'all. What do we say? We get this ball rolling. Welcome again to Masterclass Live. Today we are talking about assessing mRNA and LNP quality attributes and impurities. My name is Paula Ohrens. I'm a market development manager here at SCIEX. I have hosted quite a few of these masterclasses, but I can tell you wholeheartedly today is probably the one I'm most excited for. We have a jam-packed agenda for you over the next hour, so I hope you are comfortable in your chairs or standing wherever you might be listening to us in the lab. Before we get started, I wanted to introduce a couple of things to you. We will be pausing for questions throughout the entirety of the session, so you should see at the bottom of your screen there is a Q&A box. Please feel free at any point to insert a couple of questions into the box. You can also chat me if you'd like. If we don't get an opportunity to answer all of your questions throughout the session today, we will be able to follow up with you after the fact. So please don't hesitate to ask any questions in the Q&A, in the chat, whatever you are most comfortable with. We have a lot to talk about, as I mentioned. We're going to provide a bit of an overview at the start of why the analysis that we will be doing today is important. Then we're going to go into those details. So you will see firsthand how to process or characterize the 5' cap of mRNA. Then we'll break again for questions. And our last section will be on identifying LNP impurities and oxidative sites. So before I introduce the host to you, I would love to learn a little bit more about you. So we are going to launch a poll question that is just to better understand your experience with mRNA and LNPs. So as we get that rolling, I will introduce you to your speaker today, your host. Matthew Stone works as a SCIEX biologics workflow specialist that focuses on business development for life science research and biopharma applications. He received a BA in chemistry at Carleton College in Northfield, Minnesota, and later earned a PhD in biochemistry from the University of Minnesota, where he developed protein derivatives of factor VII with enhanced activity as potential enzyme replacement therapies. He did postdoctoral research at the National Institute on Aging using mass spectrometry-based functional proteomics, and also worked at the University of Minnesota Center for Mass Spectrometry and Proteomics core facility, working on various collaborative proteomics-based research projects. Personally, Matt is one of my favorite technical experts, so I'm thrilled that you're all going to get a chance to experience that knowledge firsthand. So Matt, how you doing today?
I'm good. Yeah. Thanks for the introduction, Paula.
You're welcome. So why don't we go ahead and get started, and you can kick things off and let everybody know the importance of what you'll be sharing today.
Okay, great. Thanks again. Great. Yeah, so, this session is going to focus on mRNA, LNP, either for vaccines or for therapeutics, and the characterization of these type of modalities. So this is a picture of mRNA encapsulated or a lipid nanoparticle with mRNA encapsulated within it. And as you can see, it's a very complex structure. There's several different components that need to be characterized. Certainly the genetic material itself, confirming the sequence, and then mRNA has it has a 5' cap and a poly A tail that would need to be characterized as well. The lipid component also needs to be characterized, and so on and so forth. There's certainly you can do bioanalytical assays on efficacy. Is my mRNA producing the protein? What kind of yield? Are there any off-target effects? So on and so forth. But in today's session, we're going to focus on just a couple of these types of assays by LCMS, and that's going to be the 5' capping assay, as well as characterizing some of the ionizable lipids that are within these components. Yeah, and I would in my view, the 5' capping assay is a relatively routine assay. You don't need a necessarily high-end, high-resolution instrument to do it. But what I want to showcase today are some of the tools within the SCIEX OS software to automate and streamline the process to assess, the yield of your your fully capped species. For the ionizable lipid component, this is going to be maybe more of an advanced type of assay. Where we're going to share data on the SCIEX's newest or flagship instrument called the 7600, using electron fragmentation to distinguish oxidative impurities. So kind of what I call a more routine assay, and something that maybe maybe a little more advanced. So when I for 5' capping, oftentimes this is done with an in vitro based system, and the 5' capping process is pretty complex. It's performed enzymatically with several different enzymes, and I'll show pictures of this in the next slide here. But there's several intermediate products within this process, and the goal here is to essentially quantify the percent yield of this process. Do I have X amount of fully capped species, within my reaction? And so this is a diagram or the mechanism of the capping process itself. So it starts with 5' end of the mRNA here with a triphosphorylated species. A guanidine group is added on here, and then there's a couple of subsequent methylations to form the fully capped species that we call cap1. In regards to the lipid work, so this has really been inspired with the observation here on the right hand side, where naked mRNA, if we look at a chromatogram here, comparing a naked mRNA with mRNA extracted from a lipid nanoparticle formulation, what we can see here is that there's some species that are later eluders that's kind of been a mystery to what's going on here. And Moderna came out with a paper later last year, where they implicated that the ionizable lipid, tertiary amino ionizable lipid, can get can be oxidized to form an N-oxide species, and this species can then go on to result in an aldehyde that can covalently modify the mRNA itself, rendering it inactive or non-translatable. And when you look at an ionizable lipid over here, if they're certainly susceptible to oxidation. This looks like a kind of a forced oxidation study here, but this would be a main peak of the ionizable lipid itself, and then some of these early eluders show different oxidative species. And the question here is, can we characterize these different species to discriminate some of these oxides that may be more problematic than other ones? And so with that, I guess I'll pause here.
All right. I do have 2 questions, one that I have actually answered for everybody to see in actually, I don't know if it'll come out in the chat or in your Q&A box, but just to let everybody know that we are focusing on mass spectrometry and the use case of it for mRNA-based therapeutics today. But I do have a second question for you, Matt. Mm-hmm. Can you comment at which levels N-oxides are impacting mRNA efficacy?
Yeah, that's a good question. I think some of that's unknown, but just in talking to people in this field, the problem really resides. It's like a stoichiometry problem. When you consider mRNA that maybe has 2,000 bases, for example, or like an saRNA that could have 10,000 bases, for example, there's just several, there's just so many bases that if one of them gets modified, it could have a detrimental effect on translation. So it kind of comes down to some of these impurities, even if they're at low level, they could be fairly problematic because of that stoichiometry issue there. So there does seem to be a need to be able to characterize them at fairly low levels.
Awesome. Okay, that's it for now. So why don't we get into it, and why don't you show us how to get it done?
Okay, great. The purpose, or what I'd like to impart on the folks that are attending here, are basically a couple of features within the software to help streamline some of these processes that are either within the core software of SCIEX OS, or that are add-ons to SCIEX OS. So this is a homepage of SCIEX OS software here. SCIEX OS is it has a couple different functions. It has it's used to acquire data on the newer 𝗀𝘆𝘀𝗃 products from SCIEX, and it also has some processing components to it as well. So again, this is the homepage of the software here. On the left, it's all tile-based. On the left is all the acquisition features. Here are the processing features, and over here are management features. I do want to mention that the software is compliant ready. There are user role definitions can be added, as well as audit trail features as well. If I click on this configuration button here, this is where the licenses are located within the software. So my version of SCIEX OS, I'm sitting at home in my home office here. So I have the base SCIEX OS software, and I also have what we call the Intact Quant add-on to the software as well, that I'll discuss in this in the webinar, or in this session. So just going back to the home page, the base software comes with Explorer, which is this is our characterization software, as well as Analytics, which is our quantitative software. Those that are not familiar with SCIEX OS, but maybe familiar with SCIEX, Analytics encompasses multi-quant for quantitation, and Explorer encompasses a couple different modules, but Peak View is one of those modules. Molecule Profiler is an add-on to the software. I have it here in my version of SCIEX OS. Molecule Profiler is our MetID and impurity software. I'm not going to discuss this today, but I do want to mention that there have been tools added to it for oligonucleotide analysis, specifically around impurity analysis. So, what I've noticed with some of the 5' capping assays, when you do an RNase digest, sometimes you get, I don't want to call them impurities, but sometimes RNase HS or RNase H provides some other components, like some 3' -1 components. And so Molecule Profile can automate the identification of those types of impurities. But again, I'm not going to showcase this software in this session. All right, so I'm going to start with 5' capping, and all this is 5' capping is really a quantitative analysis. I just want to use Explorer to review the data, so I'm going to open up the Explorer here, and this is a chromatogram of an example 5' capping assay. So again, this is these are digested fragments, and I'm going to have different species within this material. So I'm just going to zoom in to where these components elute, and this is essentially all the components within this time window right here. And if I zoom in this M/Z range, I can see some multi-charge species here, or different charge state species. And I see some commonality. I'm going to zoom in a little more here. I'll zoom in on this component here, so you can see some, the isotopic resolution here of one of these capping intermediates. A couple of things I do want to point out within the Explorer software that I think are useful. So I'm going to just go back here, and in BioToolkit there is an add-on feature called, BioToolkit itself. This tab is an add-on feature to the base software. And this allows you to do reconstruction or deconvolution of charge state series. So I like to use this tool just as a quick check to make sure the deconvolution is working well, and to confirm the identity of some of these components. So I'm going to reconstruct these proteins. This is my starting mass, mRZ range to my stop range. I'm going to use a fairly well-resolved example here. Because we are using a high resolution instrument, and but we can also look for average mass as well. So just hit OK, and this will give me the reconstructed or zero charge state species here. This is the doubly phosphorylated uncapped species. The difference here is a difference of 80, so this would be the triply phosphorylated species, and over here are some of the capping or the capped species. One thing that's kind of nice about the software that I like to use is if I just select this peak here as an example, this reconstructed peak, it'll show me the charges that this data that was used to calculate this data. And I come from a protein background. Sometimes in deconvolution, you can get artifacts or harmonics, and this is just a nice way to, hey, yeah, I have a nice repeated charge state profile here, and I am I am using, I'm not, for example, I'm not using charge state series that are not represented in the raw data. So, again, that's a nice little feature within the software that I like to do as a QC check. But I've already copied down, in this assay, we should know what the targets are. So I've already copied down these different components. So I'm gonna get out of Explorer here, and I'm gonna, I can go back to the home page, or you can go right here to analytics. This is our quantitative software. And so I'm gonna show how we would set up a processing method to to assess the yield of the CAP1 species. So hit new here. So this is analytics, again, is the quantitative and screening software within SCIEX OS. This is going to be a straight quantitation experiment. So this workflow, I'm going to unclick this and click on here to do a quantitative experiment. I just have to load some representative data in here. So I'm going to go to my mRNA folder. Whoops, went too far. And just select that folder there. And we'll select one of these files. One thing I did forget to mention during the session with an Explorer, looking at the raw data, this is kind of a contrived experiment where we spiked in some of the components. The fully CAP1 species is only like 20% or 25% of the material. So, it's a good example of, being able to identify various components. All right, so now that I've selected a file here, I'm going to go to the components tab. And as you can see, we can you develop a method by just walking through these different, the different features here on the left. Click on the components tab. And this is where I can start defining components. This default components sheet here, this is really designed for an MRM based method. So you can enter your precursor and your fragment ion masses here, to do an MRM like method. Or, if you were just doing a TOF-MS type of quantitation, you could add in just a precursor mass, for example. But what I'm going to show here is the use of the intact add-on within SCIEX OS. So I'm going to go to options here and click on mass reconstruction. And what this will do is now I'm going to quantify off of, instead of like a single species or an MRM type of experiment, I'm going to quantify off of mass deconvoluted or reconstructed data. So, here I can start filling in the different components. This grouping here is what we're going to, because we're quantifying several different species here, I'm going to define a group and keep it, within one single group, because we want to basically sum up all of the different species within the different capping intermediates, and then define that as group one, and then quantify the total area or the percent from that total area. So that's why I'm going to use group one here. And then here I can start, adding in the different capping intermediates. So in this data, I have doubly phosphorylated uncapped species. I'm going to just, I've already defined this. So my expected molecular weight is 7903. And then, I can put in a retention time that I expect it to be at. And from the raw data, I've already identified these. And then the mass reconstruction area, these are, somewhere in between 7,000 and 9,000 species. So kind of continue down the line here. And I'm not going to fill out the entire the entire component list, but we can add in things like adducts, whether if you have sodium adducts or potassium adducts, for example, so on and so forth. This is be an addition of 22 or so. So I'll do that, and we don't have to be too exact here. The next tab is where we'll get a little more. We'll provide a little more specificity. But again, just want to define the components that we want to calculate off of. All right, I'm going to throw in the GCAP here. GCAP is 8328, and here is 11 point. Actually, this is 11 point. We'll call it 38. So the GCAP, actually, the addition of the guanosine, we do get a little bit of separation within the peaks, so that elutes a little later. And similar with the adding the methyl groups, that causes a little bit of retention time delay as well. All right, I'm just going to add in 4 components here just to make it simple, because I know you guys don't necessarily want to see me typing for the entirety of this. For this session. All right, so now that I've defined these components, I'll move down. Oops. I'll move down over to the integration parameters. So this is going to perform an initial integration here. From the data file, I'm sorry, an initial mass reconstruction from the data file I selected. And then, what you see here is we have the different components that I defined. Here's a chromatogram. Here is the 𝗭𝗲𝗪 scan, and here is the deconvoluted data over here. And then here are the different parameters that can be used to reconstruct as well as to integrate those peaks. So, first thing, I'm going to uncheck this. This kind of tripped me when I was first doing this, but make sure to unclick this recenter on the largest XIC peak, because it'll just it's assuming that everything is eluting at the same time if you have this one clicked. So there's a couple different options here. There's a lot of flexibility within the software. In this case, the resolution for reconstruction is 2500. So this would be reconstructing an average mass. We can change this, to reconstruct and have isotopic definition. It just depends on what you feel most comfortable with in quantifying. So for this doubly phosphorylated uncapped species, I can zoom in over here, and you can see we're integrating the the whole isotopic series here. I can go to 30,000 here, and then we'll show integration with a singly defined isotopic species. So again, it just kind of depends on what you're how you want to quantify some of these peaks. But we can go through these different species. Yeah, I do want to apply the change. And I think I may have well, it's going through the reconstruction process again here. I may have clicked on something. Again, I'm going to unclick these. Yeah, so you kind of get the idea here. But essentially, we can look down here, and I got to unclick that and apply there, because it's centering around the most intense peak here, and so it's using the wrong retention time. All right, so here's my fully capped species. There's cap 0. I also have GCAP in there. So that's an example of how you would set up the integration as well as the reconstruction parameters within the software. I can then go to calculated columns, and this is, so I'm going to add a formula here. So this gives you the option or the ability to add in custom calculations. So I'm going to sum all the areas. So I'll call this sum area of all the different components. And here I'm going to, I already have a formula that I've written down here. And you can kind of see the logic here. I'm going to get group area of component 1. Again, we've defined every single species here as group 1. So basically just grabbing all the peak areas here and summing them together. I only defined 4 components within my components table, so I'm going to get rid of that last one. And then now I have my sum area, accept the changes in return, and I'm going to add another formula here, and this is really going to be percent 𝗀1, which is really what I'm interested in for determining percent yield of these different components. So this is a fairly simple calculation, just a percent area calculation, and I'll apply that one, and then I can define some flagging rules. So I'm going to add a rule here. And this is going to be a custom rule. And essentially, you may have some, acceptance criteria of, I need to have, for example, 90% or 85% of 𝗀1 species, before moving on. So I'm going, or, to consider the reaction completed. So this will be percentage of 𝗀1. This is going to be the column here that I'm going to define. And the flagging criteria can be a range. I'm going to set an upper limit here. This is going to be values by component type. So I'm only really concerned about the 𝗀1 species. So I'm going to put in, I don't know, 85, something like that. I could do this for other species as well. If you want to see the disappearance of an uncapped species, for example. But essentially, what I want to be, what's going to happen here is when I process the data. And we look at the summary table, it's an easy way to see, is my, do I have sufficient 𝗀1 or not? So from here, I'm going to close this out and actually open up some process data. But essentially, these are the different steps and different tools that are available within the analytics of SCIEX OS to do this type of analysis. All right, so this is what the process data looks like. So let's see, I'm going to move this over here. Actually, so here's the different component names here. Everything is linked to the bottom here. So I can, as I'm reviewing the data, I can highlight one of these and I get all the, the information on, from the chromatogram, from the mass spectra, as well as the deconvoluted mass spectra to kind of review the data. What you can see here is that, my flagging rule, showed that my percent of 𝗀1 is only 25%, and therefore it flags a blue, it's not to the 85%. So I can, again, you can quickly review the data, see there's a blue flag there, and then go to the fully capped species and say, yeah, everything looks good. The integration went well, but I just don't have I don't have the right percent yield. Some other things that are nice about the software is that I can change, if something went wrong with integration or didn't pick the right peak, or not the whole peak wasn't integrated, I can change some of these integration parameters on the fly without, for a single component, without, setting or changing the global parameters that I initially set. So with that, I am going to pause here. And so hopefully this kind of shows how to develop, how to make a streamlined method to automatically process and get percent, yield of these different capping species.
Awesome, Matt. Looks good. So I'm just going to take a quick second to remind everybody, if you've got any questions, please feel free to pop them into the Q&A box and we will address them in the next 30 minutes, or otherwise I will contact you after the fact to make sure all your questions are answered. But I've got 3 questions for you, Matt. Okay. So first up is, can I use this methodology for polyA-tail analysis?
Yeah, I think the, polyA-tail, it can be, either template derived or it can be enzymatically derived. So there may be some different needs there in terms of what you want to get out of the data. Certainly you want to, certainly there's going to be a need to get, the extent of the polyA-tail, the distribution. Oh, thanks. That sort of thing. But the question may be a little different. It may not be a percent yield calculation. It may be, just more of a distribution type of thing. But you can certainly do kind of a similar process. The experiments can be similar because you're gonna digest off the 3' end of the mRNA to a shorter piece that can be, that can be analyzed by LC-MS. And then you can define, a component of, where you think the center of that distribution should be, and some components that are that have different extents of annihilation. And then, you could set up a custom calculation, for example, of the ratio of, where you expect that, the middle of that distribution should be versus the edges. And you put in flagging rules and that sort of thing, in case that, the distribution is off. And then again, obviously you have the 𝗁𝗲 data to go back and confirm.
Awesome. All right. How do you account for the differences in ionization efficiency between those variants for quantitative purposes?
Yeah, so I didn't. I think, basically this is it's a relative quantitation method. If you did, you could certainly, add in an internal standard or make a quant curve. I see, some, yeah. So if the ionization efficiencies, you can account for that. I see it more of as kind of a relative percent check. And that's kind of what I've displayed there.
All right. One more for now. Can SCIEX data be processed with non-SCIEX or third-party tools?
Yes, I think, a lot of the quantitative data, I think SCIEX has really good tools for that. But, there are, other soft, for example, some of our impurity analysis or metabolism analysis, we can use mass metacyte, yeah, basically the answer is yes, depending on what you want to do. I don't want to necessarily promote, certain softwares over other ones. But, for the most part, we do work with third-party software.
Cool. All right. Why don't we put a pin in questions for now and we move on to LNP impurities?
All right, so here's my component screen from the 5' capping assay.
Yep.
I'm gonna go to Explorer again, and so this data was collected on our 7600 instrument using electron fragmentation. So I'm going to close these guys, and I'm going to open up, and this was done with an ionizable lipid called MC3. So we'll choose a data file here. This is a raw material. I'm going to open this as a standard TIC. So this is a raw material. So we expect to see a main peak here. And this data was information dependent acquisition, or this is what SCIEX terms as data dependent acquisition. This is a real, kind of a survey or a discovery type of experiment. And, we weren't sure what we'd find in this. It was the first time running it. Ultimately, we wanted to assess the impurities. But this data was essentially, kind of, we got the material, set up a data dependent acquisition experiment, and then basically process and examine the data in more detail. So the fragmentation technique is electron fragmentation. I'm going to remove the MSMS traces here just for clarity. Here's the main peak here. The main peak, I'm going to click around it, double click on it, just to open up, the data that lies within or underneath that peak. In the middle here is the survey scan, or the base peak survey scan data, and you can see that we have 642 is the the dominant precursor here. And this is the molecular weight that we'd expect for MC3, the pure raw material MC3. And then down here are the different MSMS scans that are used, that are from the data dependent experiment. So down here I can toggle through different MSMS events and then take some of this this data down here to for structural characterization of the lipid species itself. I actually prefer, or I think there's some utility to use another tool here. And so what I'm going to do is actually go up here and use what we call IDA Explorer from the Show tab here. IDA Explorer is a map of the different MSMS triggers within the experiment. And then, from here I can, look, hey, I want to make sure I have, I want to characterize this main peak MC3 first. This is eluding at 15.5 minutes. So I'll zoom in here. And I have this nice bright blue peak here that is the MSMS trigger of MC3, of that main peak MC3. So I'm going to click there, and that will populate the EAD MSMS spectra of that main peak. So I like using IDA Explorer for this because what we can do here is we can merge spectra with similar precursor masses. And so in this experiment, I think it's only like a top 2 or top 3 data dependent experiment. So we are collecting, we're triggering, a few times across the peak. And by, merging some of this data together, we can average, we can get an average MSMS spectra of the different triggers, and that can reduce noise as well as, potentially give us a little more mass accuracy and that sort of thing. So instead of, going spectra by spectra, I do like this feature I do like the IDA Explorer feature. All right, so, so let's interrogate this MSMS spectra in more detail. I'm going to hide the other panes here. And, again, this is electron-activated dissociation data. And I'm going to zoom in on the y-axis. And this blue arrow here, this is, this defines, or this labels the peak. This annotates the peaks. So I'm going to drop this down because what you can see here is that EAD data produces, pretty information-rich mass spectra. And if we want to be able to take advantage of all these peaks to structurally characterize the main peak as well as different lipid components within here. So from here, what you can do is you can open mol files. So I'm going to open. I have some predefined mol files here. So here's MC3 itself, and what you can see. So this is the structure of MC3. This is a mol file. It's got the head group with the tertiary amine and a couple of isomeric alkenyl groups. And another thing I'm going to do is I'm going to show a fragments pane. And so this produces theoretical fragments or in silico fragments from the structure that can be used to match to the experimental data. And so basically right here I can drag this mol file to the experimental data, and it'll match peaks based on this experimental data. Up here, what we can see is the blue peaks are peaks that match to my theoretical list. The red peaks don't match. There's a couple of features here that I do want to point out. So this 320 peak is actually a doubly charged peak from the precursor. This is actually a feature of electron detachment or electron detachment that didn't result in a fragment ion. So this is just a doubly charged. It's not a proton addition. It's actually an electron detachment or an ejection of electron. And all these other red peaks are similar doubly charged peaks for these species up here. So here are the different fragment options that are available here to define your in silico list. MC3 does have a couple of double bonds here, and electron fragmentation will fragment through a double bond. So I am going to unclick that because we will fragment double bonds. We don't have any rings, so I don't have to worry about that. The maximum number of double bond or the maximum number of bonds to break. I've set it at 1. Certainly there's going to be, especially at the low mass area down here, there's going to be fragments that result from multiple fragmentation events, but just for simplicity and clarity, I'm going to leave this at 1. We're going to allow radicals because electron fragmentation does result in radicals. And we're going to set the mass tolerance of the MSMS data, pretty tight because this is a high resolution instrument. So we want to take advantage of that and be confident in assigning peaks here. And so, so that just wanted to kind of show you some of the different options there and during your in silico list. Now, so right now the experimental data is linked to the mol file here. So there's a couple of different things I can do. I can draw around different structural elements of the molecule. So I'm going to draw around the head group here. And what you can see is it'll calculate the theoretical mass of that head group, and it'll show me where I should expect to see fragments that match to that feature. So if I zoom in here, what I can see is I have a fragment here that's matched in blue at 132, and it's spot on here. So we have the head group here that's matched. If I zoom out here, we have the concomitant, or the other fragment that would result from fragmentation along this carbon-oxygen bond that would define the rest of these alkenyl groups. So if I zoom in here, sure enough, we also have a fragment 9 here at 511.5. And that's kind of another nice feature of electron fragmentation compared to collision-induced dissociation. CID, you tend to get, one side of the molecule tends to grab the proton, and you don't always get to see both sides of fragmentation. Electron fragmentation, because it is more of a radical process. Oftentimes we do see both sides of a fragmented bond. So, and I will tell you to keep in mind this 511.5 peak, because it is diagnostic for the for these 2 alkenyl chains. So I'm going to just zoom in here at the higher mass region. Again, here's the 511 peak. The other thing we can do with the software is you can just highlight across a peak, and it's interactive. And so in this case, this peak in bold here is the in silico predicted fragment to match there. And when I do that, we see differences in mass of the other, from this peak to the other features that are within the MSMS spectra. So for the next peak here, I see a difference of 13. And that's consistent with there being a double bond right here, because the next fragment here should be a C, it should be a CH group, and that would represent 13. So if I, click across that peak there, sure enough, that represents a double bond, or the CH group right here. The next species should be CH2, and that should be 14. And that's exactly what we see here is a peak that's 14 mass units different. So that's consistent there. The next peak should be 13, and that's what we see here, and then 26 across that double bond. So essentially we can use this data to basically confirm the different structural elements within this compound. I can even go in here and circle around the head group or the tertiary amine. And if I zoom out here, this gives me a predicted fragment down here, and then another fragment up here for the rest of the molecule. And sure enough, we get this 599 peak that represents everything except for that tertiary amine. So this is great. We basically confirm the structure of the main peak, but what I'm really interested in is characterizing some of the impurities. So I'm going to go back. Actually, I'm going to close this window here. And go back to my chromatogram, and I'm gonna whoops. I'm gonna duplicate another graph here because I want to have a comparative mass spectra. I'm gonna go back here, and I'm gonna do an XIC of this chromatogram and look, specifically for oxidative impurities. So I've already set this up. We're going to look at the survey scan data, just the top MS scan data up here, and I can specify my peaks I want to extract. So I've already done this. I have the main peak MC3 that's at 642. I've defined that compound. And then I added 15.995, which would be an oxidative impurity or incorporation of a molecular oxygen. And I've got that here as well. So I'm going to perform the XIC here. And again, I just want to hunt for some of these oxidative impurities and see if we can elucidate their structures. All right, so here's my XIC down here. It's no mystery that I have this main peak MC3 here. But if I kind of zoom in down here, let's see, we see in pink here that the pink traces are the XICs of the oxidative impurity. So I see peaks down here that are, around 1,000-fold or so lower intensity than the main peak MC3. And, question is, can I define, where oxygen is being incorporated within these two different species? All right, so I'm going to go back to my, IDEA Explorer. I'm just going to hide some of these panes here. And those peaks were at 13 or so. So I'm going to zoom in at 13. And so here I have the different MSMS spectra for the early eluting oxidative peak and the later eluting oxidative peak. I'm going to click on this, that triggered event there to produce the MSMS data over here. And then I'm going to hide this pane here and compare these two spectra. Again, I kind of want to define where this oxygen is being incorporated. I can add this spectra to the top here, and now I've overlaid these two spectra. I'm going to hide this one, and the other thing I can do here is I can make this into a butterfly plot. So I'm going to select invert second overlay. So the main peak MC3 data is much more intense. So I'm just going to reset the y-axis using the % button here. So that's easier to visualize, and I'm going to zoom in on the y-axis to look more closely at some of these structural features or MS or fragment ion features. And what we can see here is that we see this common fragment ion at 132 that I talked about before. So this kind of indicates that the oxygen incorporation is not within the head group itself. Again, we do have a mass difference of 16 here in the precursor. And then some new features start to pop up here at the higher end of the spectra. And if I zoom in, we see common fragment ion here at 545. Then all of a sudden we see this unique peak at 586.5, 601, so forth. So this is so it appears that the oxygen is being incorporated somewhere towards the end of the alkenyl chain. And then, I'm going to remove the MC3 data and then kind of do what we did before, open up the mol file and see if we can define where that oxygen actually is. So here's the MC3 mol file again. I am going to open up my fragments pane, kind of like I did before. And we'll zoom in a little bit here. Yeah, first of all, again, I can draw around different structural elements. We'll draw around the head group, and we see that nice 132 peak here that I described before. That represents a head group. So again, it doesn't look like oxygen incorporation is occurring over here. But if I look for that concomitant 511 ion, all of a sudden there is no 511.5 peak here anymore. And again, that suggests that, yeah, the oxidation is occurring somewhere within these alkenyl chains. All right, so let's zoom in to that high mass area of the spectra that I pointed out before in the mirror plot. Yep, so we have this 545 peak. I'm just going to go across here. And so we've kind of defined, we have a peak here that, that doesn't appear to have oxygen incorporation. And then from this 545 peak, now it seems like, if I go to this peak here is now saying it's 14 mass difference. If you recall before with a double bond, we should see a difference at 13 for a CH group there. So this is suggesting that we've lost this double bond. So what you can do in the software And all of a sudden I've got these red peaks here that are not matching to the spectra anymore. So what you can do here is I can add atoms and change bonds within the mol file. I'm going to grab this oxygen atom here and throw it over here. Again, we know there's oxygen incorporation, but we're not adding two protons. So this can't, we can't have an aldehyde here. But I'm going to remove this double bond, so I can right click and make this a single bond. And then I'm going to click on this bond and I'm going to set it to a double bond to make it a ketone. So in doing that, so pretty much because we didn't see that difference at 13, I'm pretty confident that this bond is no longer a double bond, that it's a single bond. When I've drawn this ketone structure here, these masses are now, matching. So this tells me that the oxygen incorporation is likely occurring somewhere at, right around position C6, or I guess C31 of the MC3 molecule. We've drawn different structures here. We've drawn an epoxide structure as well. The epoxide, it could be an epoxide as well. That's what we have proposed in a tech note. And I think that actually matches the fragment ions a little better than the ketone. But bottom line is, we're pretty confident that oxygen incorporation is localized right here to position, position C6. All right, so now I'm going to go back. I'm going to close this window here and close it. Yeah.
While you're doing that, I'm just going to give you a 2-minute warning.
Oh, perfect. Because this last part will be pretty fast.
Perfect.
All right, so I'm going to go back to my spectra here. We'll hide this one here. Now I want to define what this oxidative impurity is right here. So I'm going to click on this MSMS trigger, and we're going to interrogate this data here. And so what we can see right away is that I have a 148 peak along with that 132. So it looks like oxygen incorporation is occurring in the head group. We're going to just real quick here do the same sort of processes here. I actually have the N-oxide mol file drawn already for MC3. And, just a couple of things to point out. Let me show my fragments pane here as well. But, I'm going to draw around this structure, so we can draw around the head group. And, all of a sudden we have that 148 peak is being represented. So we were pretty sure that oxidation is occurring within the head group. If we go back to this 511 peak, that 511 peak reappears, suggesting that these alkenyl chains are unchanged. And I can dig, even deeper and, start drawing to get more specificity on where this oxygen is localized to. So we do see the 132 peak that's represented by this fragment ion. And then I can go in even further and draw around this peak here. And if we look down here, we see the presence of this peak at 61 mass units. That can only be explained if the oxidation is occurring within this tertiary amine group. So we're very confident that this is the N-oxide species of the MC3, and we have the diagnostic fragment ions that are the kind of the 𝗭𝗆𝗃 one at 61, along with the 511 and then 132 and the 148 pair as well. And so instead of doing this in a more in this kind of discovery type of setting, we can if I go back to this chromatogram here, whoops, if I go back to the to this chromatogram here. Now we can be very confident this is the N-oxide. This is oxidation at C6, and then I can develop an MRM based assay now that these have been characterized. And look for some of those diagnostic fragment ions in particular. Again to track and monitor some of these oxidative impurities that may be more problematic than others. And with that, I will pause.
Matt, I've got a question for you.
Okay.
Will the fragments also include rearranged peaks?
It's possible. We haven't, when we've looked at the data, we haven't observed those specifically. But I don't want to say it's not possible. I think the nice thing is that, the fragments pane that I shared, has that option, so you can look for them. But I would say that those, if they occur, they're not going to be common.
Okay. And I'm reminded now also, I've gotten a few questions about the availability of this recording after the fact. So I just want to let everybody know the recording will be available probably in the next couple of weeks. But once it is available online, then we will share the link with everybody who did register beforehand or at all, I'll say. So let me give you one or two more questions, Matt. When you have EAD MS data, can you generate a spectral library for more automated identifications?
Yeah, so the answer is yes. Within SCIEX OS software, it's actually really easy. You can within the analytics module, you can right click on an MS spectra, and you can create your own custom libraries that can be used. I will say that, when we're looking at some of these oxidative impurities, so that these are, EAD produces so many fragment ions that a lot of them are common. And I guess my fear would be that, when you do a library match, the scores are going to be pretty high because there's so many fragment ions that are going to be common. So I think probably a better approach is to find those, kind of those distinct or those distinct fragment ions that really define a structure, and use those in a more targeted MRM experiment. And the nice thing with using time of flight instrument, you're still going to get that full mass spectra anyway, even doing an MS or an MRM based experiment.
Yep, definitely. Maybe one more question. You showed an example of raw material. Can you analyze lipids from a formulated sample as well?
Yes, and we've done that before. Formulated materials are going to be a little more complex because they're going to be comprised of a few more lipids, but certainly it's not a full-blown lipidomics experiment. And certainly the instrument is fast enough, and if you have good chromatographic separation, you can certainly do a very similar analysis, to what I showed for the raw material.
Okay. So I promise not to take up any more of anybody's time. Please look forward to receiving the link for this recording over the next couple of weeks, and look for some additional masterclasses that we have planned to kick off 2023, the new year, where we will be focusing on AAVs. So I hope everybody has a very exciting end of the year. If you're in the US, a wonderful Thanksgiving, and then a wonderful holiday season and beyond. And we will see you whenever we see you next. Thanks so much, Matt.
Thank you, everybody. Thanks, Paula.